Hello everyone, welcome to my second tutorial on the steel project in which I'll be discussing about the calculation of wind load and its how to apply it in Staad.Pro. Okay, so let's get started with the calculations, manual calculations first. So now if I show the project part, first we have to calculate the design wind speed. Okay, design wind speed we have to calculate. Okay, for that, in our data sheet, we have been given some location according to our roll numbers. So I have been allotted as Kanyakumari, and for that, this wind speed, basic wind speed, which is VB, I will get from the clause IS 875 part 3, 6.2 figure 1, which is nothing but this one. So this is the map showing basic wind speed across the country. Okay, and each the whole country is divided into six parts, okay, according to the meteorological departments. So let's see what Kanyakumari falls into. So we know that Kanyakumari is here in the bottommost part. Okay, so here it is yellow color, so color scheme yellow, and basic wind speed will be 39 meter per second, right? So let's come back. So my basic wind speed becomes 39. Now the design wind speed Vz, which is nothing but some constants, okay, some factors into Vz. So this factor, if you want to know what are this, you can directly go to the clauses. But these factors K1, K2 and K3, okay, this first three factors, these three factors K1, K2 and K3 is same for everyone. Why it is same? You can go to these clauses and check. You will understand. Okay. Now only difference will come in K4 according to the location. See, K4 is nothing but a factor for cyclonic region. So cyclonic region will depend upon the location which is allotted to you. Okay. So for this, let's go back to clause 6.3.3 table 1 of IS 875 part 3. Okay. 6.3.3. So yes, okay, sorry, it's not 6.3.3, it's 6.3.4. Make a correction here, it's 6.3.4. 6.3 point, okay, so 6.3.3 is for the K3 topography, which is constant because of our ground slope. We are considering it as a ground slope which is at angle less than 3 degree. Okay, so we are not assuming it to be on a slopy ground. Okay, that is just an assumption. Okay, so 6.3.4 importance factor for cyclonic region. Now just read it here. It is given that the effect of cyclonic storms is largely felt in a belt of approximately 60 km width at the coast in order to ensure better safety. But the location is given as 60 km wide on east coast as well as on Gujarat coast. Okay, Gujarat coast and east coast. So if we see in the map, if suppose Gujarat coast is this one, right? This part is the Gujarat part, and if you are seeing for the east coast, this is the east coast, right? This is the east coast. So if your location is Vizag or Howrah, so Howrah is near Kolkata, so this all comes under the east coast. Mine is Kanyakumari. It is the southmost point. So I'll not consider it as a east point, and it's not in Gujarat. So for me, I'll not consider any cyclonic factor. But the one who is in Gujarat area or cyclonic area, okay, which is within 60 km. Vizag is definitely on the coast. Howrah is also, I don't know what's the distance from the coast. You have to see that. Okay, but most of the this one, if you're given Vizag, it's Vizag or Bhubaneswar. Then Bhubaneswar it should not be, but Vizag it's less than 60 km definitely. So if we come back to our code again, so for structural or post-cyclonic importance, it's 1.3, but for industrial structure, it should be 1.15. Our is an industrial structure. So for all of those whose structure is within 60 km on the east coast or Gujarat side, they have to mention 1.15. For the others, like for me it's Kanyakumari, which is on the southmost point, so I'll not consider anything for cyclone factor, so I'll keep it as 1. Okay, so here you have to change according to your location. Now we'll get the design wind speed by taking into consideration k1, k2, k3, k4 into vz. So I got it as 40.81 meter per second, which is my vz. Now we have to take it into account wind pressure. So the wind pressure Pz is 0.6 into Vz square. This is also this formula is given in the code. How it comes, it is from Bernoulli's equation actually. Okay, in depth if you want to see, like you need to go into the code and all, but this is the formula. So 0.6 into 40.81 square, I get this much, 999.45 Newton per meter square. Okay, remember it's Newton per meter square. Okay, so now the design wind pressure, which is PD, okay, which is PD, is maximum of Ka, Kc, Kd into Pz. Again, some factors are coming into play, or 0.7 Pz, means this is the minimum value. Okay, this is the minimum value it should be, the design wind pressure. If Ka, Kc, Kd Pz into Pz value is coming out to be less than 0.7 Pz, then you have to go to 0.7 Pz as the design wind pressure. Now let's see what is KD, Ka and Kc. Now KD and Kc, which is KD is wind distribution factor and Kc is I think terrain factor. Okay, no, it's not the terrain factor. It's let me check what is Kc. Kc is the combination factor. Okay, direction factor Kd and wind directional factor Kd, and Kc is the combination factor. So these two will remain same for everyone. Okay, you can go and check in the clauses 7.2.1 and point 3. You will get it to be 0.9 for everyone. Only change which will be coming is in Ka. Okay, according to the area what you are getting. So Ka is area averaging factor or mean area factor, which depends on your tributary area. Now, what is this tributary area? This is nothing but the rafter length into the spacing between two truss. Let me show you. If this is my rafter length, okay, this is my one rafter length, right? Into the spacing between these two truss. So this will become the area. Okay, right? So my rafter length is, this rafter length was 9.64 total rafter length, and my spacing was 5. So I took it as 9.64 into 5, which is 48.2 meter square. Now what to do with this tributary area? Let's see from table 4 of clause 7.2.2. If I see 7.2.2, yeah, it's here, the average area factor. So it depends on the area, tributary area. Now my area is 48.2 meters square. So it falls between 25 and 100. Now I'll interpolate and I'll check, I'll get my area averaging factor. So it is like it will vary from student to student according to your tributary area. Okay, so just interpolate and get your Ka, and just this will vary. Okay, Kd and Kc will remain same. Now I got Ka as something point 0.4, what 0.86 I got something. Okay, I got something as 0.86, and then I calculated my PD, maximum of this two. Okay, maximum of this two. Let me show in the project file also. Maximum of this two, and for me it was also coming as the same case that this for everyone I think it will come as this only. Might change that Ka, Kd, Kc, Pz value will overpower this 0.7 Pz value, so you will get definitely this, and this will be your design wind pressure. Okay, design wind pressure. My design wind pressure was I guess 700 something, 703. Okay, I'll, you will see in my calculation I have mentioned it, 703 here in the force calculation, 703.5 Newton per meter square. Okay, now this was the your design wind pressure. Now let's come to what to say, calculation of pressure coefficients. Okay, now why pressure coefficient is needed is because your angles, the inclination at which wind is hitting is neither 0 degree nor 90 degree. because in the clause it has been mentioned in table 6, tables, not here, sorry, table, okay, table 6, okay, it's not coming, let me scroll down. Yes, this is the table 6. Even in, I think I've not mentioned it in my PPT. Okay, no problem. So table 6, you can see that uh, the external pressure coefficient CPE, it has been shown that is like in the last video I've said that truss is divided into a four parts, okay, four quarters, EFGH. Suppose at one point wind is hitting at 0 degree, okay, and one end it is hitting at 90 degree, for which you have the values. But in general it will not hit at 0 or 90 degree. Instead it will hit at some angle, okay, it will hit at some angle. For that we need to see this table and get our CPE value, that is external pressure coefficients. Now how to check this? This is nothing but H by W ratio. H by W ratio is nothing but, as mentioned here, H is the highest lift, okay, and W is the lesser horizontal dimension of the building. And H and W is given in our data sheet. For me, H was 8 meter and W was 18 meter. So I got 0.44, which is less than 0.5, which is nothing but our first case. If you see here, building to height ratio was less, H by W is less than half, okay. So my case falls in this. It might be that your case falls in second, and it might not fall in this, of course, okay, it can fall in this, but for me it had fallen this first case. So my roof angle was 21 degree, so I have to interpolate between 20 degree and 30 degree, okay, because we have values for 20 degrees and 30 degrees. So we will be interpolating it between those. And here you have wind angle at 0 degree at EF and GH side, and wind angle for 90 degree at EG, okay, at EG and FH. Now what is this? Okay, you can see here EFGH and EGFH. Now when wind comes from 0 degree, okay, let me tell this, and when wind comes from this degree 0 degree, the windward side, that is this side, will be E and F, okay, windward side, and the leeward side, which is here this side, will be G and H. So this will be two faces, okay. Here it will come EF, and similarly here GH. Sorry for my drawing, but it's like this. This is a truss, nothing but, okay. So similarly, when we see from 90 degree, when we see from 90 degree, when we see from 90 degree, wind is flowing from this direction, wind is flowing from this direction. So for this, the windward side will be E and G, both common, okay, both common. So if this is the face of the truss, so this is here E and this is here as G, okay. So this is the face, and FH will be the rear, at the back side, okay, here this portion, it will constitute of FH, okay. So this will constitute FH. I think it's clear what is EG and FH. At 90 degree we have to consider it like this. Now let's see what is this. Now from table, let's first see about CPE, okay. CPE, okay, so for 20 degree I have the values, and for 30 degree I have the values from the table. Okay, so I have to interpolate at 21 degree. So for me it was easy interpolation. Only for one I have to do, because the other are having the same value. So it will be same as well for my roof angle. Okay, so this is the values of CPE. So the negative sign indicates that the pressure is away from the roof, which is creating a suction. Okay, suppose this is the roof Minus indicates this is away from the roof, the pressure, which is nothing but suction. And if it is positive, which means the pressure is okay, it is towards the surface, that is nothing but pressure. Okay, and it is denoted as positive. And if it is suction, which is away, it is negative, and this is positive. So keep in mind for that. And for CPE, okay, CPE is CPI is nothing but internal pressure coefficient. Okay, and for this, uh, sorry, for this we are considering why only plus minus 0.5 is there are various three cases considering wall opening as first is 0 to 5%, second one is 5 to 20%, third one is above 20%. Since it's an industrial building, we will consider it to be for everyone will consider this value only 5 to 20%, so that CPI is plus or minus 0.5. So with the help of this, we'll get four cases. Okay, four cases. What are those? At 0 degree, at theta is 0 degree, and CPI is plus 0.5. So from the table we have CPE, which is nothing but the external, was minus 0.36. So it's suction. So away from the surface. Similarly, 0.4, it was minus, so we are showing it as an aware. We'll not write plus or minus here, we'll just show it by arrows, okay, with the direction. So 0.5 is positive, 0.5 is positive, but it is for the inner surface. For the inner surface, it is acting towards the surface. Okay, so it should be in this direction only, it should be in this direction only. So the resultant of 0.36 and 0.5 will come out to be 0.86, because CP net is CPE minus CPI. So minus of 0.36 minus of plus 0.5. So it will become nothing but minus 0.86, or we can show it as 0.86 in the suction direction. Okay, upward arrow. Similarly here in the GH side. Now, how to calculate? These are the coefficients. Okay, keep in mind these are the coefficients which have no units. Now, how to calculate the force? It is given by a formula which is written in the code. Okay, F is equal to CP net area into PD. Now, area I have showed you tributary area. I think you remember that tributary area is 48.2. Okay, which was nothing but rafter length into spacing. And CP net you have got here, CP net you have got here. Okay, so this one F will be at intermediate nodes. This is F of EF. Okay, this is F of EF. Let me show it with the project. Okay, so this is what is the force. uh, yeah, this is on E. When we are calculating on EF side, suppose this is minus 13.58 or 13.58 with suction, we have to write here. Then load on end and top nodes will be half, we have seen in the last video. And why it will have, it will be half, I have shown you. I think it's not included here, but it will be half. We know that here, here, and here it will be half. Okay, and at load on each intermediate node will be just 13.58. Okay, load on each intermediate node will be 13.58 suction. Similarly for GH and EF. Now comes the second case. For case number 2, we have theta as 0.5 and CPI is minus 0.5. See, CPI is minus. So when we see from inside the roof siding, it is creating a suction from inside. So it is pulling it here. Okay, it is creating a suction from inside. So it is 0.5 because it is internal. Okay, and this is external 0.36. So external, from external it will be like in this direction, and from internal suction will be from this direction. So if you see, if you do this one, so it will be 0.5 CP net is minus 0.36, and minus of minus, that is plus zero point 0.5. So it will come out to be plus 0.14, and plus denotes pressure, okay, directly on the roof. So it will be like this, plus 0.14 towards the surface. Similarly for this side. Okay, and force, you know that it will be This one 7 point, suppose any value at this node, okay, at intermediate nodes and the end nodes, it will be half. Okay, so now let's come back to the case 3. Okay, case 3 is at 90 degree. This is important. Everyone tends to make a mistake here. Given as theta is 90 degree and CPI is plus 0.5. Now since it is some values of EG is given, okay, some value I've got from interpolation as 0.7 and 0.7. Now what we do is, suppose this is my value, I write 0.7 on one side and 0.6 on one side, but it should not be made. Okay, because EG, as I have said, it is on the same side of the truss. So at the both the sides, okay, this is nothing but a same side. So EG, because it is exposed. See here, EG is exposed to the 90 degree side. Okay, it's nothing but on the same side of the truss. Sorry. So it will be same pressure coefficients on both the side. If you are writing opposite, the professor will think that you are making a mistake just by looking at the figure. So keep in mind that when you are having at 90 degree, whether it will be in any case, when the wind is hitting at 90 degree, at both the sides it will be same. So here CPI is plus, so I get 1.2, 1.2. Okay, so for FH also we are having something like, again for FH will be the backward side. Okay, backward side of the truss. Like suppose GH will be here, EG will be here, and FH will be in the middle somewhere. So it definitely in the middle the wind will be less. Okay, at the ends only wind will be critical. So suppose here the coefficients are 1.1 and 1.1. So we'll not consider this while like for manual calculation though we can write it, but while applying it to Staad, we are not required because it will take time and it's of no use, because we know that if it is like 1.2, it is safe in 1.2, it will definitely be safe in 1.1. So it's of no use to include this. That's why I'll not include this while doing it in my Staad. Similarly for case 4. Okay, so case 4 also is in the same manner. Although we can neglect the entire case 4 itself because this is so less, 0.2, you can see from all the cases it is very less. Okay, even case 2 is very less. Okay, but we can't neglect it right now because we are in the learning phase. So we should add all the cases except we'll not consider this one, FH. Okay, we'll just consider the first part. Okay, so we'll be getting the loads, we are getting forces on each member. Okay, and wind will be as a member load. Okay, it will not be as a nodal load like that of dead load or live load. So it will act as live load at the member load. You can see from the project. Okay, we are calculating here. So this is all for the truss, this loads, not for the columns. Till now we have done only till truss. Okay, so and this is the different load combination, I'll talk about it later. First let's go to Staad. Now uh, the last example which I was dealing, I made a mistake in the geometry. So this time I'm taking into account my project which I have did. So we have did till live load, right? Now is the time to include wind load. See, we are having four kinds of wind load. Okay, because we had four cases, right? We had four cases, so four different kinds of load will come into play. That's why four different cases. Now, okay, suppose I'm at now how to add this wind load. Here again same procedure, add. Okay, suppose under it's some number and it is wind. Okay, type here as w, wl1, add. Okay, again wl2. Okay, and so on. Close it. Okay, I'm just for time's sake I'm just including two loops, wl and w1. I'll delete it later on because I've already assigned those, just for showing you are doing this. Now coming to w1. Okay, forget about all this load combination, I'll tell you. Now just think that you have two loads, w1 and w2. Okay, So first click on W1, sorry, W1 and add. Okay, so now this will be as a member load. Okay, member load, and it will be a concentrated force. Now the direction will be in the local direction, okay, not in the global direction. Gy means global y and y means local y. Now the force direction, if it is suppose, let's put some values whichever we are getting from our load cases. Okay, whichever we are getting from our load cases, and okay, suppose here it's 7.29. Okay, and it's suction, so it should be away from the surface. So let us put 7.29. Let us put 7.29. Okay, and here it should be d1 is 0, d2 is also 0. D1 is the distance. Okay, at some time you have to put the mid distance also of the length, but not now. Okay, keep it a little bit. So added. Okay, again one, we should also add the half forces. So d1 will be again half it. Suppose I took it as 7.3, then rounding it off to half, it will become 3.65. Okay, add again 3.65. I am taking it as at a load. D1 will be, suppose my rafter length is 2.41, so 2.41. Okay, 2.41. Why 2.41 I have taken one more combination is, I'll tell you later while I am doing it. Okay, I have taken. Okay, so there are different combination. Okay, we have got this. CP net. Okay, for GH side also we have to do like this is 0.9. So similarly you have to add, get the force with the help of that, and you have to do it. Okay. So let's close it. Okay, wind load for 1. Okay, now let's use the cursor to assign. Suppose, now before that you need to know what is the, okay, sorry, where were we here? So you see here you are seeing some question mark sign, integration sign. That means till now you haven't assigned this load. Once you assign the load, it will turn into green. Okay, so that's the sign. Now you need to know what is the start and end of the member, each member. Okay, and in the last class I discussed that if it is green, so that is the start of the member. Start of the member means that is nothing but d1 is equal to 0. Okay, because the member will start applying here. Okay, at the start of the node. Suppose, see, you can see here d1 is the parallel distance of the loads from the starting node. Okay, so that's why if I put 0, it will act at here, it's at the node itself, right? So that's why I am keeping it to be 0 here. Okay, so let's assign my load. Okay, assign. If I apply at this node, it will assign here, it will assign here, it will assign here. But here I should not assign, because here it will come half, right? So here I can assign. Okay, but here I shouldn't. Let me undo it. Okay, I can assign here, here. Oh, what? Sorry. Okay, yes. So this load I have assigned. Now see, you can see that these are in the upward direction, and we have given us positive values. So that means when we are giving us positive values, it means, see, this is the y direction. Okay, this will be the y direction. So for that it will be in the positive direction only, because upward is nothing but positive. So when you have to give pressure, you need to put minus. Okay, you need to put minus, which is in our case 2. So that will become pressure. Now here we know that in our case 1, we had suction. So that will be nothing but in the positive direction of y, the local y direction, so in this direction. Okay, so in the similar fashion, here we will put this load only in this portion, okay, eg, because it is up to eg only. For fh you need to again put here fh for that load, not fh, sorry, what it is, ef, sorry, ef only will be applying. For gh you need to calculate from its coefficient the force. Now again 3.65 at 0 meter, okay, half load, okay, at the end node. So if you see, uh, if I apply here, okay, if I apply here, yes, it has been applied because this was the starting node, okay. But if I apply here in this member, it will assign to this node itself, but I don't want that. This load should be here at node number 2. So for that, undo this, okay. For that I need one more load which is at a distance of 2.41. Okay, so d1 will become 2.41 from the starting point. Okay, so now when I will assign this to this member, now see, it comes to this node. Now you understand why we have to put at 2.41. Okay, why we need to take at this. So you need to add load for this portion also, so do with that. Similarly we have to do with, we have to add other loads, that is w2, w3, w4, okay, right. Now I will show you the load combination. We have added all the wind load, that is w1, w2, w3, w4. Let me delete this because this is not my load. Delete. Yes. Now coming to load combinations. Okay, we will never consider the individual load. Instead, we'll go with load combinations as prescribed by IS code. Okay, in IS 456, you will find in the table this load combination. What are the different load combination? Let's see here. These are the 19 types of load combinations. First the individual nodes, okay, this individual nodes, then 1.5 dead load plus live load, then zero point 0.9 dead load plus 1.5 wind load. Zero point 0.9 you might not be remembering, but it is due to the seismic load or reversal of loads. The dead load will decrease, that's why factor of safety will decrease. So this is one case, okay. This is one combination. Again 1.5 dead load plus wind load 1. We have to take into consideration all the possible conditions, okay, all the conditions whichever is possible in at that number, we have to take into account and we have to add it in the stat. So these are different types of 19 types of load combinations, okay, till now. So this, only this we have to add right now. So first is this one, dead load plus live load. For now, how to add load case detail? Again add, here it is define combinations, okay, define combination, and suppose give some load number, okay, and suppose you give it here as 1.5 uh, dead load, okay, sorry, okay, this is the name actually which will be presentable here in the tab bar. 1.5 dead load plus live load, right? So select dead load, keep it here, sorry, dead load, okay, sorry, what, first dead load, select live load, select, okay. For both the thing, the factor is 1.5, 1.5. I have added, right? You can see here it has been again added 1.5 dead load plus live load, okay. So it will automatically take values from here, load 1 and load 2. Now let me remove this, delete. Now let's come to 1.5 dead load plus wind load 1 in the similar fashion, the same thing, okay. But see, suppose I, one trick is mentioned here, okay, something, add, define combinations, okay. Suppose it's 1.5, okay, 1.5 dead load plus wind load 1. All the wind loads separately you have to consider. Now dead load is 1 and wind load is number sorry, first dead load select, Wind load is you need to select. You can either default it here. If you put it default here, then it will by default take into account this factor. Okay, so keep it as one. You can separately add like type here also. You can see here, if you apply this, okay, no, it has not taken into account actually. I have to 1.5. Okay, 1.5. It's not changing. Let's delete. Okay, load case detail, add undefined combination. Okay, 1.5 dead load plus build load 1. Okay, dead load goes here, wind load 1 goes here. Default, suppose I put it as 1.5. Okay, let's not keep it as here. In the from the next time we can keep it 1.5. Okay, let's keep it as 1. We'll change here 1.5, 1.5. Add, close. So you get the combination here. Now again we have to repeat it 3 times to get it up to wind load 4. So it becomes a little bit tedious. Okay, for that, for shortcut, go to where it is, utilities, and go to the command file. Okay, now you can see such kind of thing. You can come to your load combination number 20, which is this, and here, as you can see, copy paste this. Control C, enter, paste 3 times. Okay, so now see here, first one was when load 1. 1 denotes the first load, which is the dead load, with the factor of safety 1.5, and this 3 depicts which was the load number of wind load 1. Okay, now for wind load 2 you have to change here 2, and here you have to change 4. Why? Because when we are taking load, okay, when we are taking load, we can't close once we are in the editor. Okay, once we are in the editor we can't change. Okay, because dead load was 1, live load was 2, wind load 1 was 3, wind load 2 was 4, like that. That numbering we have to keep, then only Staad will read that. Okay, so here it's 5, and here also just keep it as 3. Okay, here 6, here 4. Okay, so now you have defined, this is nothing but the codes. Okay, so once we're modifying the codes, Staad will automatically get updated. So control save, it turns into green, close it. Okay, 6 error. Okay, fine. Okay, something load combination. What does this errors? Some errors are coming. Okay, there are some, I did some errors. Okay, I did some errors here. Okay, so 20 was 1.5, that was 1.5. Okay, so what is the error reading? Load combination 1.34, combination step 20. Might be because I've already defined it here, that's why it's showing it as an this one error. But once you start it from the start, it will not show like this. Okay, it will definitely work. So you can see the effect. You can see the effect. Suppose let's move and go to the loading. You can see the effect. Oh, now I understand why it's not showing, because I have already defined some loads which were here. Okay, which were here, like what to say, 1.5 dead load plus wind load 1. So I already defined this one in like 1.5 dead load plus wind load 2, 3, 4. That's why it's not coming, because it doesn't want repetitions. So but you will be doing it from the start, so it will show. So you have to change like you have to add your loadings in the similar fashion in which I did here. Since I have already added, it's not showing. Okay, so let me delete this also. Now coming to this again, this combination 1.2 into dead load plus wind load, then this 0.9 dead load plus wind load 1. This in the similar fashion you have to add such these loads. Now this is the load is completed. Okay, come to the analysis. Okay, come to the analysis, define commands. Okay, or you just go to analysis commands. Okay, put to all in the performance analysis, everything will be printed here. Okay, add. Okay, close, go to the design section. Okay, and here put steel. Okay, and in the current code you have to put is 800 2007 LSD. Okay, not working stress design but from the limit state design. Okay, you have to do that, and then you have to define some parameters, which is nothing but fu and fy value, which is nothing but the fu and fy value. Fu is for 10 MPa. Okay, you have to do that. Since I've already added, no need to add again. And again in fy value, where is fy yield, that is ld, yield limit is 25 and 250 MPa. In kilonewton per meter square it will be this much, so you have to add. Okay, then you have to apply it in all those things. Okay, and then you have to put some not this one, steel take off. Okay, first you have to put in check code. Okay, check code, add, then again put a command take off. This will like make into account the total weight of the steel members. Okay, it will calculate. So put take off and close. Okay, suppose steel takeoff is there, I have selected all the members and assigned it. Like you can see, I have assigned it to all the members. For check code also I have assigned it to all the members. Okay, assigned it to all the members. I think I wait a minute. Yeah, I have defined my fu and fyld. Okay, I have defined my fu and fyld. So this is up to the design, and you can close it here. No, not close it. Let's run the analysis. It will ask for save. Okay, you'll get the output file. Okay, so see, zero errors and some warnings. Warnings are nothing but because we are taking this as an planar truss, that's why. No, nothing to worry. If errors are there, we need to worry. Now let me first delete, like, okay, no need to see. You can see this output file first. Okay, you have got everything. Now we have to extract the forces to do the worst combination table. Okay, on each member, worst combination table, right? Now there are various way to extract the forces. The first method is where is it? Yeah, member forces. Initially you will not see this member forces, right? You will not see this member forces actually. Where is it? Oh, wait a minute, I need to show you. Run analysis, view output file, done. Okay, so if this member for doesn't comes, you go to at the end that performance analysis, and you can yeah, when this performance analysis comes, you can write a code. It's not showing. Okay, read only. Why it's showing read only? I think some problem is coming inside, otherwise it will not show as read only. Okay, you can edit this one. Oh cha, okay, okay. We need to change it in the utility. Sorry, utility and command file actually. Okay, in the command file, you go to the performance analysis. Okay, or this performance analysis. Yes, here, because I have formed the performance analysis again, so it's showing again the analysis. I have did it first here. Okay, so to obtain the extract the forces, you have to type this. Okay, you have to type, I have already typed. Okay, load list 7 to 90. Okay, 7 to 90 means the loads which I have mentioned here actually. Now don't open actually. Okay, go to the loading. This is the numbering actually, 1 2 3 4 5 up to 19. So we need only to consider about the, what to say, a combination, because this individual loading will not give that effect. Only combination we have to consider. You can consider this, but no need to do, it will take time and it's of no use. So you can do it from 7 up to 19. So go to utilities, command file, go up to the performance analysis. Okay, then right here you can see here two times performance analysis, because I have done multiple times, so don't worry that you have one, it should be only one. No. Okay, so you have to write this code. Let me zoom in. Load list. Okay, load list 7 to 19, which means from 7 to 19 I need the list of load, and print member forces. Okay, print member forces. Then you need to save, close this, and then when you go to the output file, when you go to the output file, you will see here the member forces. Okay, for member number 1. Okay, for member number 1. Okay, so at join 2 and 1, so for combination 7, load combination 7, this is the axial forces. Okay, this is the axial force. This is the shear. Actually shear will not come, but it is coming only due to eccentricity, because that d2 value we are not giving exactly actually. Okay, so there will be some eccentricity, but we will ignore this because these are very very small. Okay, but ideally it should not come. So only axial force we have to consider. Okay, this row. So you could see that at member 1 you have this loads. So one procedure is, you could see, or you could go to the member, and you can see that what is the maximum positive and what is the maximum negative from this table, and write it down. Okay, now how to see what is maximum positive and what is maximum negative? Okay, now see, this is the method. You need to extract forces from here only. Okay, I'm going to close this. For all the members from this one, all the members from load 7 to 19 is given here. Now suppose if for member, if you want to know the member. Okay, see, it's beam 2, that is member number 2, with starting node as 2 and ending node as 10, right? So I come to the PowerPoint. Okay, so load or node, suppose I've taken member 2, and this is the start node. Start node, how again say, by green. Okay, by green. So green is the starting node and blue is the ending node. So the start to end direction means in this direction, it will give you the positive x direction. So if there is any tension forces in this direction at this node, so it is in negative direction. So that means don't see at 10. Okay, don't see at 10. If it at 10 it is in positive direction, then also okay. Try to see at the starting node. So if it is away, like in the opposite x direction, that means it is minus. Okay, minus. This is nothing but just a convention, right? We are just using a convention that we see the starting node and tell. Don't mix up. Okay, don't mix up that for one member you will see starting node, and for the other member you are seeing this as the starting node. Suppose this is one inclined member and you are considering this as starting node, then things will get mixed up. You need to either do it from a starting node or you need to do it from a ending node for all members. Okay, for all the members. So keep in mind this one. You need to either consider from starting or from ending. And from start to end, this is positive. Okay, not in the other way around. So I have taken from starting, so my tension is negative because see it's on opposite, so my tension is minus 62, like this is the negative sign I'm seeing. Now the second method is go to the post processing, okay, and go to this beam results, and then the maximum axial forces, okay, you will see here, okay, you will see here, and then again the same thing, you can abstract loads from here, it will give you the maximum forces, okay, it will give you the maximum forces for beam number 1. So maximum positive or negative forces, right? You have to get positive forces, only the axial force it will give, okay. So you can copy and paste this, suppose for beam number 2 I am taking, okay, beam number 2, so copy paste up to only member 2, once one member at a time, copy paste, copy, control C, open Excel, paste, okay. Suppose this is the member, member, this is the load combination, uh, this is delete this, delete the distance also, delete this, delete this, okay. So for only for member 2, and this is the load, okay. Now what will be the design load, design load, okay, for tension side, and one is will be compression, okay, compression will be positive and tension will be negative. So tension will be equal to minimum of, minimum of all these values, come down, come down, come down, all this combination is given here, okay. So see minus 134 to is minimum, in within seconds you can get the design loads, okay. And for compression is equal to maximum, oh, sorry, maximum, again select all this, you will get maximum of this, okay. You can do by any of the methods, you can extract the loads by any of the methods. So this is the maximum compression load and this is the maximum tension load, okay. This is the maximum compressive force and tension load. So design load for member number 2, in the worst combination table we can write this maximum, like the design load in tension and compression is so and so kilonewtons. Now one more method you can see is still, okay, deleted, okay. Now one more method is you can go to the reports, okay, sorry, first you need to go to the analytics, okay, utility, sorry, post processing only, be in the report, go to the reports, first you need to select this beam, okay, all the frames, all the beams in here, sorry, okay. So first you need to select all the beams, okay, only the truss member, and go to the reports, okay, beam end forces, okay, beam end forces and axial force, okay, axial force, click ok, you'll get this table automatically, okay, you'll get this table automatically. Copy this, select this, copy, go to Excel, control V, okay, and delete these tables, okay, delete these tables, this table, this table, this table, because we don't need this, we need only axial forces, okay. Even shear we can delete this, okay, and design load, let it, delete this, okay. So let us see what this gives us, okay. So this is load combination and this is the nodes, load nodes. Sorry, I want to go to the beam and properties, axial force. Okay, so what this gives us? Okay, axial force node. Okay, right. So in member beam this. Wait a minute. Let's check this. Okay, at a beam 25, for beam 25, you can filter it out. Okay, you can filter it out. Okay, you can filter it out. Filter by selected cells value. Okay, then for suppose you want to get for member number 5, click here OK, and for load combination, okay, all the loads for node 5. Okay, suppose you need to check which is the which is this load first, which is this member number 5. Okay, so check here where is the member number 5. If you want to get to know the member, okay, shift M, apply shift M. Wait a minute, go to analytic modeling, shift M. uh, yes, shift B, actually shift M will give you the material, shift B. So this is the members. So where is 5? 5 5 5, where is 5? Yeah, 5 is this actually. Okay, and this is beam number 5. Okay, so this is nothing but the central tie. So in the central tie, see where is the starting node. Starting node is here at the topmost. And what is this node? So let's see. uh, Close this, shift B and press shift N. So 6 is the starting node. Now if you select starting node as 5 and do your calculation for this as starting node 5 and for others for another node, then it will create a mess. Okay, you will get wrong results. You need to check first which is the starting node. Here the starting node for my is 6. Okay, so I will go here and I will go to load and I will check only 6. If I go for 5, then I will get opposite values. Okay, so now you can do again the maximum of all. You can calculate maximum and again minimum you can do here. Okay, right, you can do. Now you can see in load combination 5 2 6, hey, it is coming at to be 0. Okay, only in combination we are getting some values. Okay, in that manner you can extract it from all the forces. It will be very easy in any method you can do. Okay, so let me show you what we have to add in the worst combination table. Okay, worst combination, what we have to take the worst combination table. Suppose first put serial number. Okay, then let's go to member name, then let's go to type of member. Okay, type of member, then member length, member length, okay, and then you can just you can abstract from there. Okay, all the maximum negative load you can either do in this manner that you will write all the load combinations. Okay, all the load combinations, write down their members here, or you can do it the other way. You can just calculate your dead load, live load. Okay, sorry, I mean separately for each members, and then you enter it here. Okay, uh, so what will I do is that uh, let us add all the combinations, or no, let me do it just the worst combination. Let me add worst combination. worst combination. Okay, worst combination, and this will be the design load. The design load. Okay, and one will be in tension, the other one for compression. Okay, so suppose in member name, if I write member number 2. Okay, and what is the type of member? Okay, let us check. Member number 2 should be, where is here? Here member number 2 is a tie. Okay, so right here tie. Right tie. Member length we know. Worst combination you check which is the worst combination. When, like when you get the load, you check with which load is it corresponding, which combination is it corresponding. Write that load here. Suppose it is at 1.5 dead load plus wind load 2, so write that here, and then write the design tension and design compression. Okay, so for like this, do it for all the members. And suppose it is this member. Okay, suppose this is this member 15 member. So this is an sling. Okay, this is an sling, major sling. So you need to write it sorry, you need to write it here as, suppose what was the member, member number 15. Okay, suppose member number 15. Okay, first complete all the ties and then go to others. I'm just writing it down. So it's a major sling, major sling. In the similar fashion, do it here. Okay, so I have also described in my PPT what are the different members: major sling, minor strut, major struts, rafter, central tie, major strut, tie. So in this, just in that fashion only, we have to complete our dead worst combination table. Or you can also do that. You can just write all the types of combination. You just copy paste from there, and you can do the filtering here itself. That is also one type. Okay, any way you can do. Sir said that in any method you can do that. Okay, so that was all about wind load. Okay, I hope you really liked the explanation. If you have any doubts, you can ping me. Okay, I will be happy to clarify that. So thank you.